Right now, the entire artificial intelligence revolution, every autonomous vehicle navigating city streets, every generative model writing code is basically completely dependent on a single company pouring concrete in the Arizona desert.
Yeah, it's wild to think about. We usually picture software when we think of the future, right?
Exactly, just lines of code floating in the cloud. But the reality is shockingly physical. It requires extreme heat, literal atomic-level precision, and billions upon billions of dollars in infrastructure. So welcome to today's deep dive. We are looking at TSMC, the Taiwan Semiconductor Manufacturing Company.
And specifically, we are unpacking their historic second quarter 2026 earnings call, their latest financial reports, and that breaking news regarding their massive U.S. expansion.
Right, because we want to figure out how one company is practically single-handedly building the hardware infrastructure for the rest of the world.
We have a really critical stack of sources to go through for this. We are synthesizing their Q2 earnings transcripts, official management presentations, the financial releases, and pulling in some geopolitical context from CNBC and the New York Times.
But before we get into the mechanisms of how they're actually doing all this, I need to look right at you, our listener, and say this. All the information and analysis we discuss here today is strictly to help you better understand the market. It is not investment advice. Investing involves risks, so please ensure you do your own homework before entering the market or consult a professional financial advisor.
That is super important context. Our focus today is strictly on the mechanics of the business, the underlying technology, and the strategy. We're not doing market speculation.
Okay, let's unpack this. We have to start with the sheer scale of the Q2 2026 financials, because honestly, you cannot understand their future strategy without looking at the massive amount of capital they are generating right now.
It really is staggering. For the second quarter, revenue hit roughly 40 billion US dollars. That is over 1.2 trillion new Taiwan dollars.
Wait, 1.2 trillion?
Yeah, which represents a nearly 34% increase year over year. But the figure that really stands out is the net income. They posted a 77.4% jump in net profit year over year.
Which is just, how does a heavy manufacturing company, one dealing with raw materials and physical factories, achieve a profit surge that looks like a software company's growth chart?
Well, it comes down to unparalleled pricing power and operational leverage. TSMC's gross margin is pushing nearly 68%.
Wow.
Right. And in semiconductor manufacturing, your biggest enemy is the depreciation of your equipment. Those extreme ultraviolet lithography machines cost hundreds of millions of dollars each.
Yeah, they aren't exactly cheap.
Not at all. But once a mature fab, say, one producing older 16-nanometer or 28-nanometer chips, is fully paid off, it becomes a pure cash machine. And those mature nodes heavily subsidize the astronomical costs of developing the bleeding-edge technology.
And looking at the breakdown, the market is aggressively demanding that bleeding-edge tech. Their advanced technologies, which they define as 7-nanometer and below, now account for a whopping 77% of their total wafer revenue.
Yeah, it's a huge shift. Specifically, 3 nanometer is 30%, 5 nanometer is 33%, and 7 nanometer is 11%.
And 2 nanometer is sitting at just 3% right now, right?
Correct. It's just in the early stages.
So to explain this simply, if these chips were a city, are smaller nanometers basically like building tighter, taller skyscrapers to pack more processing power into the exact same city block?
That is a great analogy, actually. Yes. But at 2 nanometers, you are practically fighting quantum physics.
Like electron leakage and immense heat.
Exactly. So they had to transition away from older transistor designs to what is called a gate-all-around, or nanosheet architecture.
Wait, gate-all-around? What does that actually look like?
Think of the transistor channel as a wire. In older designs, the gate that controls the flow of electricity sat on 3 sides of that wire. But at 2 nanometers, the gate fully wraps around the channel on all 4 sides.
Oh, so it gives them absolute maximum control over the electrical current.
Exactly. It prevents that electron leakage you mentioned and drastically reduces power consumption. It is incredibly difficult to mass produce, but completely necessary for what the market wants right now.
Which brings us to the massive platform shift. Because for the last decade, TSMC's earnings calls were basically dominated by smartphone demand, right? The latest iPhone cycle was the heartbeat of the company.
Oh, totally. But the sources show high-performance computing, or HPC, now makes up 66% of their revenue. It grew 20% in a single quarter.
While smartphones have dropped down to just 22%.
Right. And that's because HPC is the engine room of the AI revolution. Every large language model, every generative AI tool, and every hyperscale data center requires HPC chips.
Because the smartphone market has largely plateaued, right? While
Yeah.
AI is just in this explosive infrastructure build-out phase.
Exactly. AI requires the most advanced, power-efficient architectures possible just to process the sheer volume of data needed for training models.
That shift makes perfect sense, but it actually highlights a massive contradiction when we look at their Q3 guidance.
How so?
Well, if they're seeing record-breaking demand for HPC, and they're essentially the only supplier capable of delivering these advanced chips at scale, why is management forecasting their gross margin to drop? Like, they expect revenue to jump to around $45 billion next quarter, yet gross margin is supposed to fall to somewhere between 65 and 67%.
Right. It seems backwards, but this is a mechanical reality known as gross margin dilution.
Gross margin dilution.
Yeah, so when TSMC ramps up a brand new technology node, like 2 nanometer, the initial manufacturing yields, the percentage of perfectly functioning chips on a wafer are relatively low.
Oh, I see.
It takes months, sometimes years, of tweaking the chemical baths and the etching processes to get the defect density down.
Wait, so are they basically just throwing away a higher percentage of the silicon in the early days?
Exactly. And when you combine that lower yield with the steep upfront costs of the brand new manufacturing equipment, the unit cost of a 2 nanometer chip is extremely high right now.
Even though they charge customers a premium for it.
Right. The underlying manufacturing cost temporarily outpaces the revenue gains, which dilutes the overall corporate margin. It's just a financial hit they have to take to establish dominance.
And the sheer physical reality of building out that dominance is staggering. They just raised their 2026 capital expenditure budget to between $60 billion and $64 billion.
For a single year. It's unbelievable.
Right. And management broke down that budget, noting 70 to 80% is going directly to advanced process technologies. But another 10 to 20% is earmarked for advanced packaging and testing. Why is so much capital flowing into the packaging side?
Because printing the logic on the silicon wafer is only half the battle. Once you have the chips, you have to connect them together so they can communicate seamlessly.
So this is where you stack the logic chip next to the high bandwidth memory chips on a single interposer.
Precisely. That's CoOSS, or chip on wafer on substrate. It allows the chips to share data at massive speeds, which is a hard requirement for AI training.
So packaging's the actual bottleneck right now.
Exactly. TSMC's customers are putting relentless pressure on them to expand this CoOS capacity. Combine that urgent demand with global inflation, and a $64 billion capex budget becomes a strict necessity.
Okay, but I want to push back on the business logic of exactly where a huge chunk of that capital is being deployed, because this leads us to the breaking news regarding their U.S. expansion.
Right, the Arizona project.
Yeah. TSMC just announced an additional $100 billion investment in Arizona, bringing their total commitment there to an unbelievable $265 billion for 4 or more new fabs. But building in Arizona is notoriously more expensive than in Taiwan, right?
It is, significantly so.
They don't have that hyper-localized network of chemical suppliers and specialized engineering talent. So from a pure margin perspective, isn't this a terrible business decision being forced entirely by geopolitics?
From a strict short-term margin perspective, yes, building outside of Taiwan carries a huge cost premium. However, TSMC is optimizing for long-term supply chain security, which is now a matter of national interest for multiple governments.
Right, and it's important we look at this objectively without taking political sides. But the reporting from the New York Times highlights this tightrope perfectly.
Oh, absolutely. I mean, we saw the Trump administration utilize tariff threats to encourage localized U.S. manufacturing. Following that, the Biden administration oversaw the 2021 groundbreaking of the initial Arizona site. And now you have U.S. Commerce Secretary Howard Lutnick praising this new $100 billion expansion.
So the reality is that the U.S. government across different administrations is heavily incentivizing or pressuring foreign semiconductor giants to build on American soil.
And TSMC is managing that pressure by positioning themselves as a vital, localized partner to their largest American clients. It's a strategic de-risking maneuver.
But does this mean they are abandoning Taiwan?
No, not at all. CEO C.C. Wei was very careful during the earnings call to clarify that Taiwan remains their center of gravity. They are actually constructing 13 new leading-edge and advanced packaging fabs in Taiwan right now.
Oh, wow. 13 new fabs.
Yeah. The Arizona expansion is massive, but Wei specifically noted that the actual construction timeline and when they pour that concrete will depend heavily on, quote, market situations.
So they are securing the land and making the commitments to satisfy the geopolitical and customer demands, but they won't fully build out the capacity until the revenue is guaranteed to be there.
Exactly. They are expanding globally, but the bleeding-edge R&D and the majority of volume production remains deeply rooted in Taiwan's hyper-efficient ecosystem.
Let's talk about the specific customer demand that is forcing them to expand so aggressively in the first place. TSMC expects their full year 2026 revenue to grow slightly above 40%.
That is an immense amount of capital flowing in from the AI megatrend.
But CEO C.C. Wei highlighted a nuance during the call that caught my eye. He pointed to the emergence of agentic AI, or authentic AI. How does an AI acting as an agent actually change the hardware requirements at the fab level?
It creates a fascinating pivot in the types of processors required. For the last few years, the focus has been almost entirely on training large language models.
Right, which requires massive parallel processing, doing millions of calculations simultaneously. That's what GPUs do.
Exactly. But agentic AI is different. It isn't just generating text, it's autonomously solving multi-step problems.
Like booking a flight or managing a supply chain, where step 3 actually depends on the outcome of step 2.
And that sequential step-by-step reasoning requires robust central processing logic. It requires a resurgence in highly advanced CPUs.
Oh, interesting.
Yeah, the GPUs handle the heavy parallel lifting, but the CPUs manage the complex logic and orchestration of the AI agents. So data centers will need a massive influx of traditional CPUs alongside the accelerators.
Here's where it gets really interesting, because almost all of those designers, whether it's an x86 architecture or an ARM-based design, are completely reliant on TSMC to manufacture the silicon, which brings up a moment on the earnings call that was almost comical, but deeply revealing.
Oh, the gross margin comment.
Yeah.
Yeah.
CEO C.C. Wei admitted he was, quote, jealous of a South Korean memory chip competitor who is currently operating with 86% gross margins.
It was a very rare moment of candor from management.
But it raises a serious question. If TSMC is the undisputed king of advanced logic chips, and they are virtually a monopoly at the 2-nanometer and 3-nanometer nodes, why don't they just jack up their prices overnight and get 86% margins too?
Because TSMC operates on a core philosophy of being a trustable partner. In a pure monopoly, the textbook move is to squeeze your buyers. But semiconductor development is a symbiotic ecosystem.
So if they hit their customers with a massive price hike, those designers might not be able to pass the cost onto the end consumer.
Right. And if the chip designers' margins collapse, they can't afford to fund the R&D for their next generation of chips.
And if the customer stops innovating, TSMC loses the wafer order entirely.
Exactly. TSMC prices their services high enough to fund their own $64 billion capital expenditures, but they refuse to price gouge their partners. They need their customers to be wildly successful, so they come back demanding even more expensive wafers.
I understand the symbiotic pricing, but they also discussed a scenario where they are actively letting competitors handle some of the advanced packaging work. Technologies like EMIB are gaining traction.
Yes, which sounds counterintuitive at first.
Totally. Letting Intel or Samsung step into packaged chips seems like leaving money on the table or giving up a competitive moat. Why would they welcome competition in packaging?
It goes back to the physical bottlenecks we discussed earlier. TSMC's CoWoS packaging capacity is so constrained that it is literally capping the growth of their customers.
So if an AI chip company wants to sell 1 million chips, but TSMC can only package 500,000, the customer's growth just stops.
Precisely. By welcoming competitors to take on some of the packaging load using alternative methods, the bottleneck is relieved.
So if someone else handles the packaging, the customer can order more raw chips.
Exactly. The front-end wafer fabrication is TSMC's core, highly profitable business. If a competitor wants the capital-intensive headache of packaging those chips, TSMC gets to print and sell 1 million wafers instead of 500,000. It's a massive strategic win.
Okay, that is brilliant. So we've broken down their current margins, their massive expansion plans, and their competitive philosophy. Let's look over the horizon, because this industry requires looking a decade into the future.
They actually provided a detailed technology roadmap during the call for exactly that.
Right, so the immediate focus is ramping up the 2-nanometer node. But looking ahead to 2028, volume production is scheduled for the A14 node, which is a 1.4-nanometer equivalent technology.
Yeah, the transistors are getting incredibly small.
1.4 nanometers. We're going to run out of ways to even measure them. What kind of performance leap does A14 actually provide over 2 nanometer?
It is a really significant jump. The A14 node promises a 10 to 15% speed improvement while drawing the exact same amount of power, or a 25 to 30% reduction in power consumption if kept at the same speed, plus a 20% gain in overall chip density.
Wow. And they are already looking past that, discussing the A13 and A12 nodes slated for 2029. And the phrase that stood out in the roadmap for A12 was in, quote, innovative superpower rail technology.
Yes, backside power delivery.
So, going back to our city analogy, is a superpower rail basically like upgrading a city's electrical grid so the skyscrapers we talked about earlier don't brown out?
The grid analogy is accurate, but to truly understand it, imagine that to upgrade the city's electrical grid, you literally have to flip the entire city upside down.
Wait, what do you mean by flipping it upside down?
Historically, both the data signals and the electrical power have been routed from the top down into the transistors. But as you cram billions more transistors into a 1.4 nanometer chip, the microscopic power wires and data wires start competing for space.
Oh, which creates resistance and massive heat, I'd imagine.
Exactly. A backside power rail physically moves all the power delivery wiring to the bottom or the back of the silicon wafer.
So you entirely separate the power lines from the communication lines.
Yes. The power comes up from the bottom directly into the transistors, while the data signals travel cleanly across the top. It drastically reduces resistance and handles the immense, sudden spikes of power required by heavy AI processing.
That is incredible, but re-engineering a silicon wafer to receive power from the bottom up sounds like it requires fundamentally altering the manufacturing process at the atomic level.
Which perfectly explains CEO C.C. Wei's blunt statement on the call that there are absolutely, quote, no shortcuts.
None whatsoever, right?
None. He stressed that developing technologies like the A14 node and backside power rails requires 5 to 7 years of relentless, continuous R&D. You have to invent the chemistry, custom build the tools, and construct the physical factories years before a single chip generates revenue.
So what does this all mean? Let's recap. TSMC is riding a historic 77% profit surge driven almost entirely by the AI megatrend. They are pouring over $60 billion a year into CapEx.
And they're building a $265 billion footprint in Arizona to meet geopolitical and customer demands, all while relying on their mature fabs to subsidize the 5 to 7 year R&D cycles required for the 1.4 nanometer era.
Exactly. And the reason you, the listener, should care about the intricacies of wafer yields and backside power rails is because this company's execution dictates our reality. Whether you are using a smartphone, relying on automated logistics, or using AI tools, TSMC's disciplined 5 to 7 year planning cycle is quite literally setting the speed limit for how fast the future arrives for the rest of humanity.
It is the physical bedrock that the entire digital economy rests upon, and that actually leaves us with a final thought to ponder. If it takes a minimum of 5 years of no shortcuts to build capacity for a single new chip generation, what happens if the AI industry's demand outpaces even TSMC's $265 billion bets? Are we headed for a future where innovation isn't limited by software, but by how fast we can pour concrete in the Arizona desert?